Welcome everyone. Thanks for attending my talk. I'm Wei Jiezhou, a PhD student from NC State. The work I'm going to represent focuses on the optimization of Python-based analytics programs, which we call HARP. These days, Python becomes the most popular programming language in machine learning domain. A common pattern in today's analytics ecosystem is Python plus X, where X represents the core computation written with APIs of libraries such as TensorFlow, PyTorch, and so on. And Python is regarded as the glue language that connects all these pieces together. Let's take TensorFlow as an example. Suppose we want to do the computation shown in red set in the TensorFlow. From the corresponding code, we can see the whole program is written in Python. When we run the program, it will first call the TensorFlow APIs to construct the computation graph. Then the computation graph will be sent to and executed by the TensorFlow backend by calling the TensorFlow session run API. This programming model represents an important category of machine learning frameworks. To optimize these kinds of programs, there already existed a lot of works focusing on the computation graph optimization. But they ignore the information from the host code and the interplay between the host code and the backend. Thus, they will miss some optimization opportunities. To address the limitation of current work, our effort is focusing on optimization of the Python plus X programming model. The result is a framework called HARP. So the core of HARP is an automatic static code optimizer with a holistic view. It bridges semantics from a host and the computation graph. It also provides a refactoring assistant that provides suggestions for developers. It allows aggressive analysis on incomplete information. Our methodology consists of following steps. Given our target program, the HARP compiler will first extracts semantics from both the host program and the computation graph. Then these semantics are synthesized into a unified knowledge base we call the augmented graph. It is represented in data log format, which data log is a declarative logic programming language. Analysis algorithms are written as query rules. HARP engine will perform these rules on the knowledge base and get the result. There are many challenges when we build HARP, such as the Python language complexities due to the dynamic feature, needs for uniform analyzable representation, needs for easy extensibility, and needs for risk-controlled feedback. Here, we can take the previous code snippet as an example to see why HARP works. From the code, we can see D and X are assigned from the host code. If we suppose D is constant, then based on this augmented computation graph, the intermediate computation T2, which represents the T times T transpose, is loop invariant. However, since the assignment of D is outside the computation graph, the TensorFlow backend is unaware of this constant semantic. Thus, it misses the opportunities to remove the computation redundancy. With HARP, with the holistic view, we can find this redundancy and eliminate it based on the host program semantics. In addition, to control the risk of uncertainty in the analysis, we provide a refactoring assistant for user to resolve the uncertainty. It not only provides the refactoring suggestions, but also the explanation and assumptions. In the evaluation, we conduct both the efficiency evaluation and the usability user study. The results shows that HARP guidance leads to significant speed up on the set of benchmarks. HARP also significantly increases participants' success rate in refactoring the programs to be more efficient. At last, here are some takeaways. HARP enables holistic analysis that spans across computation graphs and their hosting Python code. The methodology includes first, analytic conscious speculative analysis for Python language complexity, a unified representation for holistic information, at last, the conditioned feedback for risk control. From the experiment, we can see that refactoring based on HARP gives 1.3 to 3 times speed up and around 2 times average speed up on a set of TensorFlow and PyTorch programs. So that's all for this talk. Thank you very much.